In other segments, we've looked a lot at observation and description of animal behavior. Now we're going to actually look at experimental manipulation. So let's start with some examples of field experiments. This is a really old one. It comes from, I don't know, the mid-1900s, maybe even before then a little bit. But it was done by a German investigator, a German ethologist named Bruckner. And very simple. What I like about this, by the way, is that it shows that you don't need really expensive equipment to actually investigate some interesting animal behavior type problems. He was interested in whether or not chicken hens are more influenced by the visual aspect of their chicks or the auditory aspect of their chicks. So it's basically auditory communication versus visual communication. So the first manipulation that he did, as portrayed here in this sketch, is that he took one of the chicks and he put a very thick, clear bowl over it. Okay, so it can see that chick, it can see all of its chicks, but it's going to have a very hard time hearing the chick that's in the bowl. And there I just played it, might be something like that. Okay, I'm just simulating, trying to simulate what he did. Okay, and you can see the hen could care less about the sound because it probably can't hear it very well. And it's just paying attention to the chicks that are out there that it can see. Okay, fine. But now he puts a barrier up. He takes the chick out from under the cover. He tethers it so it can't run around. And the chick, of course, continues to distress call, and now the hen is directing its attention toward the source of the vocalization rather than the visual aspect of the chicks that are right there with it. And this is one of the forerunners of a lot of research that was done later in the 1900s, right on up to the present, showing the importance of auditory communication relative to visual communication, at least in some species of birds. And it didn't take much other than a clear, thick a bowl and a barrier. How do wasps remember where food is located? This was another experiment that was really, really simple. And again, it was done in the field, and here is how it was done.
We offered them tuna, presented in the center of a circle of gnomes. One yellow jacket finds the food simply by chance. As she flies off, she turns around to take a kind of mental snapshot of the terrain. Don't look back is bad advice for wasps. When she returns to her nest with food, her sisters know to fly off to seek the source. Wasps don't give each other directions. After random searching, the new wasps arrive and take their own snapshots. But exactly what will they remember about this location? To find out, we removed the food. But wasps kept coming, so they weren't attracted by the sight or smell of tuna. Next, we moved the gnomes, but not the empty serving stand. Tellingly, wasps ignored the stand and visited the gnome circle, even though they'd never been fed at this location. Did they recognize the shapes and colors of the gnomes, or their arrangement? To find out, we changed the circle to a triangle. And then we offered the yellow jackets a brand new circle of flamingos. Wasps zeroed in on the circle, even though it was made of unfamiliar objects. So wasps find food by remembering a configuration of landmarks, in this case, a circle. More typically, they remember the location of your favorite picnic table.
I mean, that is so elegant. You go out, you buy yourself some gnomes, you buy yourself some pink flamingos, and you do this experiment. And it's really, really interesting in terms of the results that the wasps are actually cluing in on the arrangement of objects around where they found food in the first place, rather than the nature of the objects themselves. Robotics have come a long, long way in recent years. Let me give you a couple examples of where we are with robotics.
So the general goal of our lab is to understand the locomotion aspect of animals. And recently we are focusing on quadruped, four-legged animals. And we try to understand how they efficiently run on the field and nature, so that we can take that inspiration and then use in our engineering world. So, for example, we can create a prosthetic legs out of that technology, or you can even make a new transportation replacing cars, so that you don't need a road in our world.
Cheetah is the fastest four-legged animal in the world. And then we would like to make our robot run fast like a cheetah. When we started to build our robot, we started to look at cheetah's motion and applied its principles to our mechanical version of a cheetah. Currently, our robot cheetah can run up to 10 miles per hour and jump over 33 centimeter high obstacle.
So previously, most legged robots are powered by internal combustion engine and then hydraulic transmission. And those are very noisy and very inefficient. But people believe that internal combustion engine and hydraulics are only way to make a legged robot runs and support itself. People believe that electric motors are not powerful enough. So this is the first time we shows that electrically powered robot can run and jump over foot-height obstacles.
In order to build a dynamic robot like a cheetah, we had to develop everything on the robot, including motors, control system, and control algorithms. Because previous robot technology is focused on controlling static motion of the robot.
I think this is a really exciting future where robot can be quiet and efficient and also powerful, and then we might exceed the muscles performance in the future.
Wow, that's amazing. I only hope these guys don't go weird someday and then unleash all these robotic cheetahs on the general public. It'll be awful.
This video is a short overview of the Quadruped Locomotion Control Framework developed at USC as part of the DARPA Learning Locomotion project. This project aims to push the performance of robotic legged locomotion to a new level. The Locomotion Controller, developed at the Computational Learning and Motor Control Lab at USC, is able to autonomously navigate and cross very challenging terrain, including obstacles and gaps as large as the full leg length of the robot.
I mean, that's amazing. Look at how smooth that motion is. Robotics have come a long way. Okay, so how can we apply this in looking at animal behavior? Well, meet RoboSquirrel.
This is what we hope the RoboSquirrel kind of looks like from the snake's perspective.
The creation of a UC Davis engineer, RoboSquirrel is a taxidermied squirrel with a mechanical tail that mimics the tail flagging movement. In this video, we see it meeting a rattlesnake. When RoboSquirrel flags his tail, the snake does not strike. But when it remains still, the snake strikes. To its great disappointment, I'm sure. Just another RoboSquirrel.
So yeah, you can use these robotic models to try to figure out, in this case, what kinds of stimuli the squirrel is engaging in that would either inhibit or not inhibit the striking of a rattlesnake. I mean, you can start to pinpoint the nature of the stimuli that cause certain types of behaviors to occur in another organism. That is so cool, I think. Okay, let's look at the sage grouse fembot.
This is a robotic female sage grouse, and the males seem to like her quite well.
Biologist Gail Patricelli is trying to figure out exactly what females look for in a mate and how the males strut their stuff. To learn their secrets, she's developed a robot in her lab at the University of California.
The most important thing that we use the robot for is to measure the display of the male from the perspective of the female. And we do that using a microphone. Okay, so the robot has a few different ways that she can move. She can move her head back and forth, and she can also crouch up and down. And she can also turn to face the male. She also has a video camera on board with a little wireless transmitter.
On this cyborg sage grouse, the feathers, at least, are genuine.
So to disguise the robotic innards, we put the real female skin on top of the robot.
Gail is striving for authenticity, but her target audience might prove to be a pushover.
The males are not that picky about who they spend time courting. We often see males on the lek trying to mate with cow pies, so the bar is pretty low in trying to make her look real, but of course we want to make it as realistic as possible so that we can elicit the most natural courtship behaviors possible.
Sure enough, the boys are soon competing for her attention. One male is putting on a really big show. There can be no doubt about his intentions. He's displaying for the fembot. Gail's experiment is working. As his calls are recorded by the web of microphones, crucial data is being collected about their volume and quality, how he aims his calls toward the fembot, and how he responds to her cues. When she approaches, he increases the rate of his calls, turning on all the arts of sage grouse persuasion.
To be able to orient it appropriately with females, to interact appropriately with females, position himself, all of these kinds of social skills that are important in sexual selection.
Yeah, this opens up a whole new arena of the wide array of data that you can collect using these forms of robotic models when interacting with live, free-ranging birds, as you see here. Really, really cool, I think. Now, something related to robotics is something new called radio frequency identification. This is kind of interesting because it enables individual identification after you implant animals with subcutaneous transponders to identify each individual in, say, a huge colony, and then you can go ahead and track them as individuals. But they typically stay within the colony depending on the species that you're looking at, and in fact this work was done with king penguins. So what they had was a radio-controlled rover, as you'll see in a moment, with a penguin chick. And the virtue of this is that it avoids disrupting the penguins because it's unlike a human approaching the colony. It's just this rover with a penguin chick. Basically, it kind of looks like a penguin chick moving along but on wheels. And it results in shorter and lower stress levels in the penguins than when a human approaches the colony. So you're doing minimum disruption of the colony when you're trying to identify individuals in the field. Now, it turns out that at first, the penguins are in fact quite disturbed if you send in the rover without the penguin model on top of it. So there's our rover, and you can see how disrupted these penguins actually are. They're very unhappy with the rover rolling into their colony. If it stops moving, actually, they'll settle down, but just a little bit. They really don't like that thing moving around at all. So that's when the researchers had the idea, and it was a great idea to actually use a model of a penguin chick and send that into the colony on top of the rover. And that's what this brief video is all about.
A team who dressed up this robot as a baby penguin. The robot on its own scared these emperor penguins, but after its fluffy makeover, they were fine with it. Some of them even tried to talk to it. Some of these penguins are tagged, and the robot is carrying a reader for the tags. The penguin robot disguise helps monitor the penguins
So those tags are embedded in the wings of the penguin. So they had previously been tagged by researchers, then turned back into the colony. And then the robot, you might have noticed there's like a little camera in the front of it. It's not really a camera per se. It's a receiver that receives the signals from the transponders. And so they can just go ahead and send this in the colony and see who is who and where they are. Okay, getting away from robots now. This is a very interesting experiment, I think, with desert ants. And basically, it's how they go about navigating. They can actually navigate by counting their own steps. Oh my gosh. So the way this is done, you train the ants on a path, okay? From their nest to a feeding site. So they're going from their nest to food. You're training them on that distance. And then in this experiment, they divide them into 3 groups. The normal legs, okay? Nothing's changed with the ants. Shortened legs, they have stumps. And longer legs, you actually put them on stilts so that they have longer legs than they normally have, as you see in this photograph. If you look at this reddish area, these are the actual stilts that elongate their normal legs. So here's a film, and you can see this is one of the elongated ants running around. And they can do it. I mean, it's just fine. It's not burdensome to them at all. There he goes. Okay, so what was done in this experiment is this. So there's our nest. You're going to train them from the nest to a food source. And it's just a given distance, okay? So there's the nest. There's X amount of distance to the food source, okay? Here's our normal ants, and they go that distance. They just, that's what they were trained to. They go to that distance, and they get food. The ones with the stumps stopped short. They had shorter strides. They underestimated the distance because their legs were shortened. The ones with the stilts, well, they had elongated strides, and so they had longer strides, and they overestimated the distance to the food. So they're basically counting the number of strides that they're taking to the food source based on what happened during training. They have this built-in odometer, so to speak. How awesome is that? Okay, let's look at some examples of lab experiments. This goes back to some very simple experiments that were done by Nico Tinbergen. He did some experiments with sticklebacks, very small fish that are found in Europe. And it turns out that the red underside of another male triggers aggression on the part of a male that is territorial. And so he would just use simple models like this, like a round disc, where he would paint the bottom with red, and sure enough, a stickleback would attack it, as if it was a real fish. Okay, but a little bit more sophisticated than that. Looking at optimal foraging. This is Nico Tinbergen's nephew, Joost Tinbergen, who I visited in the Netherlands. And he showed me what he was up to at the time. This is his lab, okay? It's in this building. And what he did was to put nest boxes, special nest boxes, in these windows. But he modified the windows. So what he did was this. He had nest boxes with birds inside the nest boxes, and he put a camera that was triggered by a photocell, such that whenever a bird returned to the nest box, it would break the photocell, causing the camera to take a picture of the bird in the opening of the nest box, bringing back food to feed its nestlings. So there we go. We have a bird that is feeding its nestlings, in this case with a grasshopper. Okay, so he was interested in just looking at what the birds were feeding their offspring. Very, very simple methodology in terms of looking at optimal foraging in the area of his laboratory. Just a simple camera setup. Well, it wasn't all that simple, it turned out, but nonetheless, it worked very, very nicely. Here's a barn owl. Barn owls are really, really cool, and they're really experts at capturing prey. Their face is like a radar disc. The ears, by the way, on a barn owl are sort of located behind the feathers up here and up here. They're not perfectly symmetrical. One's higher than the other. You can't see them. They're behind the feathers. But they can see really well in total darkness, and they can hear the slightest noise. So that's what this experiment was all about. So first, let's hear a little bit more about barn owls.
Like a shadow, a barn owl prowls through a graveyard, searching for a meal. A small vole uses the cover of dark to cloak its own hunt for food. A tiny target, it barely makes the slightest rustle, but its stalker knows exactly where it is. The owl can peer into the darkness, hear the faintest of noises, and pursue its prey in near complete silence. At night, owls' huge eyes are up to 3 times more sensitive to light than humans.
Okay, so they can see really well in the dark. They can hear really well all the time. What are they relying on mostly in terms of capturing prey? And that's what this laboratory experiment was all about. Okay, so here's the setup right here. So it was done in a lab with a rodent, a mouse. And there's a little piece of cardboard attached to the mouse with a piece of monofilament string. Okay? So there's the mouse, there's the monofilament string, there's a little piece of cardboard. As the mouse moves along the floor, the cardboard is going to make that kind of a scraping sound. So what was happening here is the barn owl initially focused its attention visually on the mouse. So it proceeds to go toward the visual object, the mouse. But then it hears the sound, and it suddenly switches its direction and focuses on what it's hearing. So those are just a really small sample of animal behavior experiments in the field and in the lab.